I mentioned briefly last time that that all of that works. If f of x, y has a maximum or minimum at x naught, y naught, then f x at x naught, y naught has to be 0. Because if it isn't, that means f is either rising or falling as you move in the x direction at the point x naught, y naught, which means if you go in the direction where it's falling, it's going to get lower. If you're going in the opposite direction, it's going to get higher. That makes sense? Should be clear, especially if you understand the geometry of tests for functions of one variable. Second derivative positive, concave up, got a minimum, and so forth. And it's got to be level at the point we have a minimum. Okay. Now, I'm not talking about necessarily a function in a confined domain. You also, as with the functions of one variable, you got to check out the endpoints of the domain to see if one of those is higher or lower than all the other points. Okay. Okay, so anyhow, ignoring that, just assuming that we're talking about a relative maximum or minimum, so maybe an absolute. You have this. Well, I'm getting ahead of myself. Stating it informally, if fx times fy is less than 0, then one is positive. The other is negative. Okay. And in that case, you don't have a max or min. In this direction, maybe the function's going up, or maybe the function's concave up. In this direction, maybe the function's concave down. And need to say if fxx and fyy is less than 0. And put enough derivatives on that. So functions concave up in one direction, concave down in the other. That gives you a saddle point. on a max or min. On a saddle point, you go in one direction, you're going down, go in the other direction, you're going up. Okay. Okay, well, even if f(x(x), fy(y) is greater than 0, in which case concavity is the same in both the x and y directions. You go up at a 45-degree angle to the x and y directions. It could be going down. You could have a saddle point. I could wave it with my hands, but it wouldn't make any sense. You think about it, you look at the pictures. It's entirely possible to have a saddle point that does that. Okay, you just rotate your saddle. And maybe it's up in both directions, but it's down if you move off at 45 degrees in some other direction. So the test fx equals fy equals 0, you have a critical point. Okay. Then you have a maximum or a minimum. If it's less than 0, you don't, you have a saddle point. And if it's equal to 0, you gotta do something else because it doesn't tell you one way or the other. If you got equal to 0, it could be either or maybe even neither. The way your text, I think, will state it, it's inconclusive. But it's a conclusive test. If you're greater than 0, it's conclusive. Less than 0. Okay. Now you might wonder why you square this one and not these. Well, it's like you got two derivatives here multiplied together. You got two here multiplied together, but they're the same one. Okay. And you can write this test. And there's a name for it. We call it the discriminant. And if the discriminant is the determinant, we'll write it like this. Fxx and fxy, then fyx and fyy. Okay. But since fyx and fxy are equal to each other, and you should understand that, having done the homework, would ask you to do it both ways. Back, earlier, last week, I guess. That should make perfect sense to you. Just the determinant. Okay, well, get that down, digest that. Okay. Now, as I said, that's all I'm going to say about this, because it's probably all I need to say. There are a couple of problems that might give you a little bit of trouble, we'll see. But they're not situations, I think, that I've seen people in this class have much trouble with. And the homework assignment just keeps asking you, for most of the assignment, last three problems, get a little into applications, okay? But, 80% of the homework assignment just gives you a polynomial in X, Y, and Z, or just X and Y in this case, and ask you to find relative maximum, minimum, critical points, do this derivative test, tell us whether we've got maximum or saddle point or something else. Okay. And if there are difficulties with anything, we'll clear it up next time we meet, which is going to be 12 days from now because of the research days. Okay, we got this thing. Okay, let's just say that this has been sitting out in the sun. Okay, and both the surface and the water are going to warm up, but not equally. It gets narrower up here. Maybe that concentrates heat up here. Okay, you got the angle of the sun, and was it shining here or here? It's been moving. Okay, so you have an uneven distribution of temperature on the, let's just say, on the surface of this thing. Okay, so one thing we could do using maximum and minimum, if that's a function of two variables, we can reduce it to that, let X and Y be parameters and parameterize the surface and write a function and use max min. Okay, just use the stuff that I just gave you. Okay, now we're not going to do that. What we're going to say is, okay, let's just say that I've got a conic section on this surface. This surface has been cut by a plane at some angle. So I've got like an ellipse, just traced an ellipse. I kind of missed it that time, but you get the idea. So I got some curve on this surface. Maybe it's not an ellipse, maybe you got a helix. Okay, you keep coming up in a helix, okay? Maybe it's some other shape. The question is, at what point on that curve, whichever curve it is, does the temperature hit its maximum and does it hit its minimum? Assuming you've got a temperature function here. Okay. Let's say we've got a surface. I'm debating. Let's just start. Now I got my notation. Okay. What notation does your book use? Which function is f and which function is g? I don't remember. I haven't looked. But I'm going to bring it up. Okay. Okay. I'm going to make this a surface g of x, y equals c. And a function f of x, y. We want to find the extrema of f of x, y on the surface. In the example I just used, your g of x, y equals c would be like the equation of the plane. Okay? That intersects this. Actually, yeah, yes. I don't want to try to make that explicit. Okay. So you have a curve. And maybe it's a closed curve, maybe it's not. But right there's your curve g of x, y equals c in the plane. At every point, g of x, y, just say at this point. So let's just say there's a point x, y, 1. The gradient of g is the direction in which g is changing most rapidly. Okay. Specifically, the direction which it's increasing most rapidly. But all we know is that along this gradient line, g is changing most rapidly. It turns out then that along the normal line or the tangent line, tangent to the surface, I'm sorry for lapsing into cursor. That says g is unchanging. Okay. in the direction perpendicular to the gradient. Now, F also has a gradient. So if we look at the gradient of F, let's just isolate this little part of the curve here with this tangent line. Here's your tangent line. Here's your point. X naught, Y naught. And here's the gradient of G. Okay. Now F is some other function unrelated to G. G just tells you where you want to look to find the maximum or minimum. G is a part of the curve that we want to talk. Or it's a path we're following. We want to know when it's going to get hottest or when it's going to get coolest. Okay. F has a gradient. We're going to postulate the angle theta between the gradient of G and the gradient of F. I claim that this can't be the point where F is maximum. Okay. Okay, so theta isn't 0, 180 degrees. F isn't at its maximum on the curve. Can you explain why? Okay, now we kind of alluded to this briefly last time. As I said, and we had a discussion of this, I'm just going to summarize it. If temperature is changing most rapidly in that direction, in what direction is it remaining unchanged? At least temporarily, it's in the direction perpendicular to that direction. This is where it's going up fastest. Back there is where it's going down fastest. Perpendicular to this is where it's not changing. The analogy was made, we could represent the temperature by a function in 3 dimensions. So you have hills and valleys. Okay. Top of the hills where it's hottest, bottom of the valleys where it's coolest, and where it's steepest, it's changing most rapidly. You stand on a hill and you can do this. There are a lot of hills. We're on top of a hill, a bunch of hills around. Okay. You walk out the door and in 1 minute, you can be on a hill of your choice. Okay. You face in the direction where the hill is going up fastest. And you say, man, I'm tired. I want to keep walking, but I don't want to go uphill. And I don't want to go downhill because I know then I'm going to have to go back uphill. Okay. So that's the direction which it's steepest. I'm going to turn 90 degrees, and now I'm walking along contour line. Does that make sense? You go out and convince yourself. And you convince yourself with symbols too. Well, okay, if we take this, that's why I'm saying that if this is g of xy is constant, that means it's not changing along this direction, means its most rapid change is normal to the curve. Okay? That makes sense? It works in 3 dimensions too. This could be functions of 3 dimensions. In which case your g of xy equals c would be, g of xyz equals c would be a surface in 3-dimensional space. You do it in multi-dimensional space. not confined to 3 dimensions, you're just confined to being able to visualize it in 3 dimensions. That's what I'm doing here. Would fail to work in a 486 dimensional space. Okay. And a lot of applications you got to think about. Guy can only think of 2 or 3 that would use 486 directions, but there are about a dozen for 487. Everybody knows that, right? Going off into ridiculous here. Seriously, you never know how many dimensions you're going to have to deal with. And you can apply a lot of this stuff to any number of dimensions. Okay, including this. Okay, well, anyhow, again, here's where G is constant. This is where you're constrained. This is your constraint. Okay, so I'll even give it the name, constraint. The gradient of your G function is perpendicular to the curve. Okay, as a curve is where it's constant, the gradient is where it's most non-constant. Those directions are perpendicular. And we have the point X all the way. Okay, so again, I'm gonna use the color here to distinguish what's going on with the F function from what's going on with the G function. So in this direction, the F function isn't changing. Okay. Now, question is, in the like direction, is that changing or not? Need more space. So I want to do some more labeling on this portion. Okay. Again, here's a part of our curve. At a right angle there. Okay. It didn't draw very good. All right, this small, this looks more like a right angle. Okay. Then we got gradient of F. And we say that F is constant. In this direction, meaning move either way on that segment. Assuming a very short segment. Okay, as we move along the segment where f equals constant is g changing. Okay, we got a good answer. A good answer was, well, it can't be because g's constant here along this direction. Of course, that would mean that the directional derivative of g is 0 in this direction, right? The directional derivative is 0 in the direction perpendicular to the gradient, because the directional derivative is the dot product of the gradient with the unit vector in your direction of motion, which we are hopefully used to. Even if we've done it mostly just with symbols, we need to understand it in terms of the geometry. Okay. Now, the intuitive answer, and it was a good intuitive answer, said, well, geez, just if you want g to be constant, you got to stay on this curve, which means you got to stay in this direction. Okay. Now, again, okay, you got a u vector in this direction. You dot that with del g, and you've got the directional derivative in this direction. Okay. And the directional derivative is going to be 0 because this vector is perpendicular to this vector. Okay. Now, if you move in this direction, your u vector, if you wish, the unit vector in the direction of motion, isn't perpendicular to del g anymore, so that g must be changing if you move in this direction. Okay. So I'm sorry, f. Okay, yeah, well, that's true. Now let me say it the right way around. You can say the same thing with f. Okay. F doesn't change in this direction. The follow of it has to change if you move in this direction. Yeah. If you move in the direction perpendicular to del g, and the angle between these isn't 0 or 180 degrees, then you're moving in a direction in which f changes. So in the white direction. So let's put a u vector along this. There's a u vector. No, I'm not sure how well you understand directional derivatives at this point, but right there is a statement you should definitely digest. Okay. Simply because the directional derivative is u dot del f. Okay. And that should be obvious, but of course, this all's fairly new to you, haven't digested it completely. So maybe we better say that. Okay. Well, what it comes down to then results in a change in F. Okay? Moving in the opposite direction along the constraint curve J equals C. Results in an opposite change in F. By opposite change, I mean, if you go in this direction and F increases, then if you go in that direction, it decreases, right? Okay. So we can conclude that F is not at an extreme temperature. That means the relative maximum or relative minimum at the point X naught, Y naught. I never did label the point, so let's just. Implicit from this picture, but worth labeling. Okay. That makes sense. You want to understand this picture. If you want to understand Lagrange multipliers, and it might be handy for you to really understand them rather than just have a formula for them. If you're trying to visualize something that's going on in multiple dimensions. Okay. Try to draw analogies in higher dimensional spaces. And you might well, depending on the type of engineering you get into, so you didn't want to do that. Which is why probably get this picture in your heads now. Okay. So wow. The way I'm going to get that board on there with the board symbol that we did. So conclusion. I'll just say that del F and del G got to be parallel. Can't tell whether the camera's focused or not. Let me back up just a little bit. The camera went out of focus, probably when it didn't have anything to focus on. But just in case, here's our picture. Okay, del G is in this direction, del F is in this direction. They're drawn so that the del G and del F are not parallel. And that's what it comes down to. Del G and del F are not parallel, and any motion in the direction of the G equals constant curve, and what we've got, the white segment is a short segment of the curve g of x y equals c. I have drawn a unit vector u along that segment. But that segment is not going to be parallel to this segment because this segment is perpendicular to del g. And segment that I've chosen here is the segment along which f is constant. Okay. And it's perpendicular to the gradient of f. It follows from what you know about directional derivatives and also kind of common sense that if this is the direction in which f doesn't change, then this is not the direction in which f doesn't change. Okay. Matter of fact, the directional derivative of f in the direction of u isn't zero unless u is perpendicular to del f, which it isn't. It follows then that whichever way you move along this curve, f is going to change. If you move this way, f might increase, so that if you move this way, f would have to decrease. Okay, or if f decreases this way, what's going to increase that way? Remember, these are short segments of continuous differentiable functions, right? So if f is changing at this point, which it, as you move in this direction, point can't be a point where the value of f is maximized on the curve. All right. A lot to digest. It's not simple, but it's not the hardest thing ever going to see either. Okay. So it's worth understanding. Comes down to this. For an extremum, these guys got to be parallel. Okay. In which case, the direction in which g is constant is the same as in the direction in which f is constant. That makes it a critical point, and that's necessary for an extremum. Follows then that del f is a constant multiple of del g. I.e., there exists some number which we'll call lambda. It's not an eigenvalue, but there's some kind of relationship. There exists some number lambda such that, geez, I don't remember which way it's traditionally written. I'm going to say del f equals lambda times del g. I could have put the lambda on the other side and still be so. I'm going to take a peek at the book and see which way they've chosen to write it. I'm not looking at the online text because I hate to look at online texts. I've got a different text here, but it's going to tell me the same thing, I think. Convention's pretty common. I haven't talked about this since last year at this time. I don't remember which way they write it. Well, purely by chance, but I wrote it in the usual way. No, it kind of looked right, so I'd give myself 60-40 on it, but no better. Okay, that's it. Well, what's that mean? Well, del f is this. If you got a function of 3 variables, then write down K components. You got a function of more variables. I'm going to use like E1, E2, and so forth for your unit vectors, and you just have to write down more of them. You got fx equals lambda gx and fy equals lambda gy. Two simultaneous equations. And it kind of appears you got three unknowns because actually fx is a function of x and y, gx is a function of x and y. And you've only got two equations. So let's just write out what we've got. For example, and make it simple. Okay, x squared y cubed. And g of x, y will be x squared plus y squared. Let the constraint curve be g of x, y equals 4. And write out these equations. Okay, so what you get here, well, this is your condition. From this, you can always write, fxi plus fyj plus fck, whatever. And same for g. Okay, so you can always write out the equations. You don't have to memorize these equations. I would memorize this and always know how it's written out if you write it out. Okay, this part's obvious. This part is the key. If you just memorize this, then you lose all your geometry. Okay? And you don't want to lose all your geometry. Maybe you do, but you get the right answer a whole lot of times, but do you really understand it well enough to carry it into the test on the test question? Do you really understand it well enough that you're going to understand as much as you might need to understand later on in your education or in your career? Okay? Does it really lock in? Even if it's going to gradually unlock over a couple of years, it'll still be there to be refreshed when you need it. So I really recommend that you focus on this and on the picture. This comes out just incidentally. And go ahead and memorize this too. It's easy to memorize. Okay, so what do we have? I'm gonna do it from the perspective of gradient. Wanted to write that 2x lambda, which is keep it in order. Understand where all that came from? I never looked at those equations, never thought about them, but that's exactly what these equations tell you. So if you just write out the two gradients and set one equal to constant multiple of the other, you don't need to memorize this. Although again, if you've done several equations, it helps to write that down as well. Okay, helps solidify your knowledge. So not discouraging these, I'm encouraging this as your focus. Okay, simple. Either way, it's simple. But if you remember why, it's much better. Okay, so now, can you solve that for x, y, and lambda? No, you only have two equations. You got three unknowns. Or you're going to get a third equation. You got one. G of x, y equals 4. So x squared plus y squared equals 4. Okay. This is a g of x, y has to equal c because this is our path. If we don't have g of x, y equals c, we're not on the path. Okay. So it's perfectly valid to include that as an equation. And I'll just solve the lambda and x and y. That turns out that's going to take a little work. Like I would solve each of these equations for lambda. Maybe I wouldn't. Yeah, maybe better to solve each equation for x, because at least the first one, x appears as a linear term. second equation for y would be a little bit complicated. You can solve it. Okay. Actually solve each equation for x and you get an equation in y. It's less complicated than what I was thinking. Well, okay, 2x y cubed equals 2x lambda. Yeah, that happens. Okay, wasn't expecting this to happen because I wasn't thinking. Okay, well, actually get lambda equals 2y cubed. We've eliminated x. Divide both sides by x, right?
What about the two?
Yeah, just y cubed. Yeah. Okay. Then lambda is just y cubed. So we got 3x squared y squared equals 2y to the fourth. So we get 3x squared equals 2y squared. Now I can get fancy. Y squared is 4 minus x squared from the fourth equation. Now we just have an equation in x that we can solve for x, right? That's perfectly legitimate. If we didn't have a y squared here, well, then we'd have to say that, and I'll do it this way to be easier and quicker to do it that way. That we could say then that x has to equal plus or minus the square root of 2/3 y. So that when we square x, we get 3 times 2/3 y squared, 3 times 2/3 2, we get 2y squared equals 2. That plus or minus means we've got to deal with cases, but that's not too bad. Okay. So now we have x squared plus y squared equals 4, which gives us plus or minus 2/3 y, quantity squared, etc. We're going to get 5/3 y squared equals 4 y squared. So y equals plus or minus the square root of 12/5. X equals plus or minus the square root of 2/3 y. Y is a plus or minus square root of 12/5. That's going to be 24/15. My arithmetic is right. And that reduces down to the square root of 8/5. Now we can check that out. If we square root of 8/5, we get 8/5 and 12/5. which adds to 20 fifths, which is 4. It's very easy to substitute these values in here to verify that we have a solution to this equation. So now we know x and y, and we also can find lambda because lambda is just y cubed. Which is plus or minus 12 fifths to the 3/2 power. And I just barely got that on the board. Getting kind of small down here, but you still understand just simultaneous equations and use whatever you can. And unless everything's nice and linear, you can't use elimination. So you got to use substitution. So now we know what lambda is. We can plug this in and check out these equations as well as this one. And if I've done it correctly, they should work. And I'm not going to mess with it. I mean, I don't mind messing with it. It's short on time. Okay. So that pretty well illustrates the process. Now, if you got double constraints and stuff like that, well, you can do it with one set of constraints. You can do it with 2 sets of constraints. Okay. And the method is easy, and people generally don't have any trouble applying the method. On tests, they always do well with the Lagrange multipliers because they forget about everything it means. And they just write down some equations and solve them. Okay, try to learn it a little better than that. Now, one thing is, what's the interpretation of this solution? You probably on the board space, but I draw kind of small. I think I would have from one of these boards available. No. Maxed it out, but this means that, well, geometrically, this is a circle. So here is strain curve when G equals 4. Okay. Notice that the gradient of G is just radial. Xi plus yj is just your radial vector. So the gradients are all radial. If you think of these functions, well, it's a little hard to really, I can't really explain it in 2 minutes. And I even have to think about it, so that's hard to think about. Okay. Square root of 12 fifths, square root of 8 fifths. Okay. Well, 12 fifths is 2.4. The square root of 2.4 is pretty close to 1.45. Well, it's pretty close to 1.55. And the square root of 8 fifths would be 1.3. Yeah, that's right. It sort of has radius. Okay, so you got this point like kind of close to 1.5, 1.3. Where this temperature function, if this is a temperature function, reaches a maximum or a minimum. Then you have a point here, point opposite this, and point opposite this, with all the pluses and minuses. Then you got to kind of test each one. Make sure it gives you a max or a min.
Okay.
And then you get a picture of what's going on. One way or another, you've got some solutions. Okay, well. Again, I don't see anything in the problems that you should have a lot of trouble with. Maybe a couple of problems will challenge you a little bit, and if they do, we'll deal with it, okay? Okay.